We're going to take a look at another example for the washer method. Again, this is important and necessary when there's a gap between the region you're rotating and the axis of rotation. The other method, when there's no gap, is the disk method, so make sure you differentiate the two. We want to find the volume of the solid obtained by rotating the following region. First graph is secant inverse of f equals x. We'll talk about what to do with that in a second. The second graph is g of x equals square root of 2. These two are going to form our region. It's going to be bounded on the interval negative pi over 4 is less than or equal to x is less than or equal to pi over 4, and we're going to rotate it around a horizontal line. Again, you should note that if it's being rotated around a horizontal line, everything needs to be in terms of x. And right now we have a little bit of weird stuff going on here with this function. We will change that around in just a second. This one is good to go because it's constant. So that leads us to our first step, initial step rather, step 0, which is to get y by itself. So right now, our f right here is not by itself. This is very strange looking. In order to cancel out the secant inverse, you have to take the secant of both sides of this equation to get f by itself. So that's what we're going to do. We're going to take secant of both sides, and I'm just doing this just to demonstrate that everything needs to be in terms of x, and your functions need to by themselves. G, f, or y, or whatever the case. So that's what we've done here, and now we have f equals secant of x, which looks a lot better than what we were given. Next, we're going to draw our region on the Cartesian plane, including our axis of rotation. So here's our axis of rotation up here, and our region is down here. This graph right here is f, which is secant of x. And then this graph up here is g of x, which is square root of 2. You can see that our axis of rotation is above our region that's being rotated. We will talk about what to do there. We've already alluded to it. We were going to detail as far as how that determines what your washer is going to be. So those are the next two steps. For step 1, we drew the Cartesian plane. Step 2, we drew our region, bounded by f and g. Step 3, we're going to draw the shape of our washer. Again, when there is a gap between your region and your axis of rotation, this will form the inside of your washer. It will be blank because there's no region there. That forms the gap of your washer. So your cross sections will look like this. This leads us to sketching now our graph with the washers drawn into the graph. So basically we're crossing the intersections of our washers and the region on the Cartesian plane. So we'll just go ahead and label this down here and color it in. This is our f of x equals secant of x. Our next region I will make a light green. That is our g of x, which is equal to square root of 2. And then we have our axis of rotation up here, which I will put in orange. And that is y equals 2. So again, you can see that the axis of rotation is above our region that's being rotated. Next, what I will do is label our two sets of washers. Basically our two radiuses that form our washers. We will have the outside radius, which again we call big R, which we'll talk about in a second. And we will have our inside radius, which we will call little r. Again, I will make that one peak. You can see that you must subtract big R minus little r, or big R squared minus little r squared, to get this area right here, which will ultimately form the volume of our solid. So this will cancel out in the middle because it's just blank space. Now, without further ado, let's go ahead and take a look and see what that volume is going to look like, or that solid. Again, we are using this app developed by Tom Brzezinski with GeoGebra. So again, thank you for making this free for everyone to use. I'm going to go ahead and rotate our region about y equals 2 so we can see what it looks like. If we zoom in here, the best way to explain this one is there is also a gap on either side. It's kind of like a ball actually when you rotate this region around, and of course it is hollow in the middle. Each of these cross sections going in between our washers, and I like the way this looks. Kind of reminds me of something I've seen on a vacuum cleaner. But anyways, it's basically a ball where the two sides have been cut. And of course, again, the center is hollow. So again, when there's a gap between your region and what you're rotating around, you will be using the washer method. So notice this bigger radius will form when you rotated a circle. You want to take the area of that bigger circle and subtract the area of the smaller. So it would be pi big R squared minus pi little r squared. Next, for step 5, we want to determine the function that's closest to the axis of rotation. In this case, it's going to be our g equals square root of 2. It's closest to axis of rotation, y equals 2. Next, you want to determine the function furthest away. In this case, it's going to be f of x equals secant of x. So this one back here. And again, we're just going to call that big F. Step 7, we will determine our little radius. Now, in this case, the region is below the axis of rotation. So to find our little radius, it's going to be a minus c. And again, the reason for that is because a is above c this time instead of the other way. So it'll be a minus c will give us this little r. So our a is 2, and our function closest we called c, or g is square root of 2. So little r will just be 2 minus the radical 2. Now to find the area of that circle to be pi r squared, so it'll be pi times this squared. Step 8, determine the big radius. So again, because the axis of rotation is above our region, it'll be a minus f. So it'll be 2 minus secant square root of x will be big R. Now, let's not skip any steps. Let's go to step 9. We want to label the radius, both radiuses, big R and little r, in relation to our washer. Here is little r, and again, it's 2 minus radical 2. And the reason we do this, again, is just for conceptual reasons. Big R is 2 minus secant of x, which is right here. You can see that if you do pi big R squared minus pi little r squared, you're finding the area of this circle and subtracting the area of this to get the area of this washer. And again, if you rotate those washers all the way around, you get this solid. That's why we integrate based on our limits. We're integrating just a bunch of cross sections. In this case, we're going from negative pi over 4 to pi over 4, which these are the decimal approximations for that. Okay, so now we want to determine the limits. Again, that was given to us in the problem, negative pi over 4 to pi over 4. And that's the range of our washer cross sections. Step 11 is to set up the integral. Again, it's pi big R squared minus pi big little r squared. You can just pull a pi out and you're left with big R squared minus little r squared inside of your integral. Then just plug in your limits of integration from negative pi over 4 to pi over 4 of 2 minus secant of x. That's big R squared. So again, you're just taking big R and replacing it with what it's equal to, which you found in your previous step. And then you're finding little r and replacing it with what it's equal to and squaring it. Making sure to subtract, don't forget your dx. Now you want to make step 12, you want to make the integral easy to integrate. Don't forget your pi that you pulled out. Basically, for this one, in order to integrate, we're just going to square both of these binomials. And you'll just do some algebra here. And you will end up with this integral right here. Okay, now secant squared is a little tricky. That comes from an integral table, which you can look up for secant squared, or you can use an advanced method you might learn in another calculus class. And integral of secant of x also comes from an integral table. Now this right here is just a constant, so the 2 minus square root of 2 squared. So when you when you integrate it, you'll just have an x next to it, because it's just a constant. Oh, this is what I was talking about. Just put an x next to it. Now again, the other two integrals or antiderivatives come from an integral table. So the final step 13 is to evaluate it. Now this one is pretty tricky because there's a lot going on, and I'm not going to spend 5 minutes explaining plugging in the upper and lower limit. Okay, it's very messy, and I doubt if you'd really be required to do this on the test. This kind of problem, you'd probably just have to set it up as we set it up right here. In fact, you probably wouldn't even have to simplify it, you just have to set it up this way. But at any rate, if you go through and do the algebra plugging in your upper and lower limit, you will end up with a very crazy final answer that looks like this for the volume. Okay, this is the one where you probably want to do it with your calculator to get an actual answer. Anyway, this is your final answer. We'll go ahead and just square it off here. And this will give you the volume of this three-dimensional shape that we generated, which again looks pretty cool. Looks like a ball basically with a hole cut in it. That's it for this particular example of washer method around a horizontal line. If you have any questions about this, let me know.